Had enough of harmonic sounds? Melodies make your stomach turn? Then I've got just the circuit for you. A triple thread of a white, pink, and blue noise generator. Before we can dive into the circuit's design, we'll have to answer a seemingly simple question. What exactly is noise? Well, from a physics standpoint, there's actually no distinction between noise and any other sound. Both are, by definition, just vibrations in a medium. So we have to be a bit more specific with our question. When dealing with synthesizers, you often hear people talk about colored noise, white noise, red noise, pink noise, and so on. This is the type of noise we're interested in here. So what distinguishes colored noise from any other type of sound? To answer that, let's start off by looking at what's usually referred to as white noise. White noise is a noise that occupies the full range of audible frequencies. To illustrate this, we'll check out a simple spectrogram of a white noise signal, where the x-axis is showing frequency, while the y-axis is showing amplitude. As you can see, every frequency is present here, in slightly fluctuating but generally similar amplitudes. Now, let's contrast this with a spectrogram of an ideal sine wave oscillation. Right away, there's a stark difference. Where the white noise signal is spread out across the whole diagram, the sine wave signal occupies just a tiny patch. That's because a sine wave is what we refer to as a pure tone. It consists of just a single frequency, unlike other waveforms which contain a wide variety of additional frequencies, also called overtones. Basically, sine waves and white noise couldn't be more different. You might even conceptualize them as polar opposites. This becomes even more apparent if we visualize them in a different way. In these diagrams, we draw pressure in a medium over a given period of time. This way, we get what you'd usually refer to as the sound's waveform. For our sine wave, this results in a smooth and repetitive shape. For our white noise signal, on the other hand, we get a chaotic, frantic, and unpredictable mess. This leads us to a more useful description of what our ears perceive as noisy: randomness. The more random and unpredictable a sound is, the more noisy it's going to seem to us. Now, in the world of electronics, sound is encoded as fluctuations in voltage over time. So, if we want to build a circuit that generates white noise, we'll essentially have to build a circuit that generates a randomly fluctuating voltage. How do we do that? Easy, by abusing a semiconductor device like this NPN transistor. As you might already know, the deal with semiconductors is that they only allow for current to flow under certain conditions. For an NPN transistor, it works like this. No current can flow into the collector as long as there's no current flowing into the base. At least in theory. In practice, if we check the datasheet for this BC548 transistor, we'll find multiple mentions of something called a breakdown voltage. There's one specified each for the paths between collector and emitter, collector and base, and emitter and base. What does this mean? Simple. It means that you can only push the transistor so far before it starts misbehaving. If we apply more than 30 volts between collector and emitter, for example, the transistor will start to conduct even when it normally shouldn't. Same idea for the path between emitter and base. Under normal conditions, current should not be able to flow into the emitter and out of the base. But if we apply more than 6 volts to the emitter while the base is sitting at ground level, the transistor will break down and allow for current to flow. Okay, but how is this helping us create a randomly fluctuating voltage? Well, as is often the case with analog electronics, things are not as clean-cut as you might assume. A transistor breaking down doesn't mean that the floodgates simply open up and current can pass through unobstructed. In reality, something far weirder happens. We'll see random, small-ish bursts of current flow through the transistor, random in timing and random in intensity. It's as if the transistor is still fighting to not break down, but can't quite keep up. Though it might feel a bit cruel, this is exactly the behavior we are going to exploit for our noise-generating purposes. Now, to actually make noise happen, we only need two components, the transistor and a resistor. Here's how it works. We connect our transistor's emitter to the positive supply voltage through a resistance. Then we ground the base while leaving the collector unconnected. The resistor serves one main purpose here. We need to convert the fluctuations in current flow into a fluctuating voltage. Why does it help us with this? To understand that, let's first assume that we've dialed our supply voltage down, below the 6 volts threshold. Now, no current flows into the transistor's emitter, because the transistor is not breaking down yet. This means that the pushing force, which a voltage essentially is, does not actually push any current through the resistor. So the voltage at this point is the same as it is above the resistor. But as we increase the voltage significantly above the 6 volts threshold, the transistor will begin to break down, resulting in random bursts of current that flow from the power supply through the resistor into the emitter and out of the base. Now, the more current flows through the resistor, the more the voltage at this point will drop. And that's because the pushing force there is allowed to transform into actual movement of electricity. This way, we convert the random fluctuations in current flow into a voltage that drops below the set supply voltage in both random amounts and random intervals. But enough theory. Let's see if this actually works. Setting it up is dead simple. Plug in the transistor, connect the base to ground and the emitter to the positive supply voltage through a 100K resistor, and we're done. To be able to see what's going on, let's check on the voltage at the emitter with my oscilloscope. At first glance, it looks like nothing's really happening, and we're just getting a steady 12 volts output. But watch what happens if I center the signal and then zoom in on it. That does look pretty noisy to me, though the signal's volume is really low. So we should probably try to amplify this if we want to listen to it. Before we can tackle that, we have to do the same thing we just did on the oscilloscope. Center the signal. That's because our amplifier needs enough headroom to be able to work properly. We'll use a standard op-amp here, which will supply with plus minus 12 volts. This allows it to operate in a voltage range that's slightly smaller than that. Since the voltage at our transistor's emitter peaks at 12 volts, we are already outside of the op-amp's range. And because amplifying a waveform basically means stretching it along the y-axis, it should be clear why we need more headroom here. So to center the signal, we'll route it through a high-pass filter. Since a high-pass only allows frequencies above its cutoff frequency to pass through, this will remove the constant positive offset from our signal. Simply because a constant offset is effectively an oscillation with a frequency of 0 Hz. Now, since we want to remove as little of our noise signal as possible, we choose a capacitor-resistor combination that gives us a very low cutoff frequency of just 1.6 Hz. Now we can send our centered signal into the aforementioned op-amp, which we'll configure as a non-inverting amplifier. For that, we put a 100K 680 ohms voltage divider in the feedback path, which should give us a gain factor of around 150. This will blow our noise signal up to around 10 volts peak to peak, the standard output level in Eurorack systems. Almost there. Now to be able to hear our white noise signal, we just need to attach an output socket to the amplifier. In order to protect it from short circuits, we'll do that via a 1K resistor. To test this, I'll first connect our transistor's emitter to a 1 microfarad capacitor, followed by a 100K resistor to ground. Then I'll set up a TL074 quad op-amp chip. Next, route the other side of our capacitor to one op-amp's non-inverting input, while setting its gain with the 100K 680 ohms voltage divider. Add in the output socket and we're ready to give this a spin. That sounds sufficiently noisy to me. Okay, one noise color down, white. I promised 2 additional colors in the title though, pink and blue. Before we can tackle those, we have to ask what differentiates them from a standard white noise signal. The answer is generally quite simple. Pink noise is just white noise sent through a low-pass filter. And conversely, blue noise is white noise sent through a high-pass filter. Once you look closer, the requirements get pretty tricky though. because both filters should have a slope of 3 decibels per octave across the entire signal spectrum, so that the pink noise signal very gradually gets quieter towards the high frequencies, and vice versa for the blue noise signal. Why is this tricky? Because a standard analog filter comprised of a capacitor and a resistor has a slope of 6 decibels per octave, and that is actually too steep for our purposes. Now, in my analog filter series, we learned that we can get a steeper slope by chaining multiple filter stages like this. But how do you get a slope that's less steep? Turns out that this is not exactly a trivial problem, because there's no inverse strategy to chaining stages. The 6 decibels per octave slope is pretty much like the atom of analog filtering. So we'll have to find a way to approximate 3 decibel per octave slopes by using some dirty little tricks. We'll start out with a white to pink conversion. For this, we'll turn our regular low-pass filter into a shelf filter with separate slopes for the low, mid, and high frequency spectrum. Now, in case you don't know what a shelf filter is or what it does, let's recap the basics here. For that, I've overlaid a standard low-pass slope with a high shelf slope in this diagram. As you can see, they are almost identical, save for how they handle this part of the upper frequency range. Where the low pass cuts off the signal completely after a certain point, the high shelf allows for a baseline amount of high frequencies to pass through. Now, how does this help us with our 3 decibels per octave slope problem? As a single shelf filter, it doesn't really. But what if we were able to apply multiple different shelf filter slopes to the same input signal? Because then we could arrange those so that the result approximates a 3 decibels per octave slope. Now, if you really care about precision here, you'd have to use a lot of shelf filter slopes to get something that resembles a smooth line as much as possible. But for me, a rough approximation is good enough, which is why I decided to go with just 3 slopes in total. One for the low end, one for the mids, and one for the high end, giving us this coarsely stepped pseudo 3 decibels per octave slope. But while this sounds great in theory, so far we don't even know how to set up a shelf filter with a single slope, let alone 3. So let's again cover the basics here first. We'll start with a simple high shelf filter. If you compare this setup to a basic low pass, you'll notice that they're almost identical, save for the additional resistor between the capacitor and ground. To understand why this little change allows a baseline amount of high frequencies to pass through, we'll have to think about the mechanics of a basic low-pass filter first. So imagine that we apply a 1 kHz square wave oscillation to that filter's input. We'll assume that the input resistor is very strong, say a 100K, and the capacitor is quite big, a 33 nanofarads, resulting in a cutoff frequency of just 48 Hz. Then at the output, we'll measure an almost unchanging 0-volt signal, silence. That's because our filter is cutting off the input signal completely, since it is way above its cutoff frequency. Here's how it works. While the input signal is in its high phase, it pushes a very small current through the resistor and into the capacitor. Now, because that current is so small and the high phase is so short due to the signal's high frequency, the capacitor will absorb it without filling up noticeably, and the voltage above it will basically stay unchanged. Why is that? Well, we could conceptualize the capacitor as a resistor whose resistance value depends on the amount of charge stored within it. That's because the capacitor is displacing the same amount of current that it absorbs. It's as if that current is simply flowing through it. But the more the capacitor fills up in the process, the harder it gets to push more current through it. Hence the resistor comparison. With this in mind, this structure essentially becomes a voltage divider. And in a voltage divider, the output voltage depends on the relation between its 2 resistors. The weaker the resistor going to ground is compared to the other one, the lower the output voltage will be. And in our scenario here, the capacitor's resistance is extremely low, because it's almost empty. Which is why the voltage above it stays close to 0 volts. And it never goes beyond that, because during the input signal's low phase, the tiny amount of current we pushed into the cap gets pulled out again. Next, let's imagine we apply the same 1 kHz square wave to the shelf filter with its additional 10K resistor between the capacitor and ground. Where before, the resistance on this path stayed close to 0, now we've got a default value of 10 kiloohms. which by the law of voltage dividers must result in a significant output voltage swing, even with our super high frequency input and an almost empty capacitor. That's because the resistance on this path will go above 10K as the cap fills up, but it can never fall below that value. So as the input signal oscillates at 10 volts peak to peak, we'd pick up a significantly quieter, but definitely audible 1 volt peak to peak signal at the output. And voila, we've set an amplitude shelf that the filter's output cannot fall below. To try this, we'll replace the fixed resistor here with a potentiometer, so that we can change the resistance value on the fly and see the effect that it has. Setting this up is again dead simple. I'll first slot in a 100K resistor, followed by a 33 nanofarads capacitor, which I'll connect to ground through a 100K potentiometer. Now we can pick up our shelf-filtered output right here. But instead of a square wave oscillation, we're using the white noise signal as an input. This will make it much easier to visualize the shelf filter's effect, because white noise, as we discussed earlier, contains all frequencies in equal amplitude. Usually, I show you output signals like these with my oscilloscope. But in this case, it's actually much more helpful to use a spectrum analyzer instead. This way, we can see which frequencies are present in our signal, and at what volume. Right now, I've got the potentiometer fully turned down. So what we see here is just a typical 6 decibels per octave low-pass slope. But watch what happens as I increase the amount of resistance between the capacitor and ground. As expected, we get this shelf whose height depends on the resistance I dial in here. And as you can hear, this means that more or less of the signal's high end bleeds through. Great, so we've got the single slope shelf filter down. Next, we'll need to figure out how to add more slopes to it. Thankfully, doing that is really straightforward. All we have to do is add in more capacitor and resistor pairs in parallel with the original one. Now, if we fine-tune their values, we should get a combined slope that looks like this. Here's how it works. As we've seen before, the amount of resistance between the capacitor and ground in relation to the input resistance will determine the amplitude at which the individual slope straightens out. Similarly, the size of the capacitor will determine the point at which it starts dropping off, just like in a regular low pass. Knowing this, we can select our component values so that all 3 slopes affect different parts of the frequency spectrum. The values I've chosen here will have our 3 slopes start at 48, 480 and 4800 Hz respectively, with their shelves set at 35, 10 and 2%. Why did I choose those exact values? To be honest, I just tried a few different combinations, and this one gave me a result closest to the pink noise examples I found online. So feel free to fine-tune these if it sounds off to you. Because the filter lowers the overall volume of the noise signal, we'll have to amplify it by a factor of about 5. Okay, let's set this up on the breadboard. First, I'll plug in 3 different capacitors, a 330 picofarad, a 3.3 nanofarad, and a 33 nanofarad. Then add in the 51K, 10K, and 2K resistors to ground. Finally, we'll route the resulting signal to this op-amp's non-inverting input, while setting its gain with a 100K, 22K resistor combination. And here's what the amplified output signal sounds and looks like on the spectrum analyzer. As you can see, it does indeed gradually fall off in volume towards the high end, approximately like a 3 decibels per octave slope would. And to me, it sounds pink enough. Cool, so let's move on to the white to blue conversion. As I said before, blue noise is really just white noise sent through a 3 decibels per octave high pass. Since a standard high-pass filter also has a slope of 6 decibels per octave, we'll have to cheat our way towards that goal with a trick very similar to the one we've just learned about. Only this time, we're not using a shelf filter, but instead, for lack of a better word, a limited high-pass. To illustrate what I mean by this, I've overlaid a standard high-pass slope with a limited high-pass slope in this diagram. As you can see, they're almost identical, save for the unaffected parts of the signal which differ in amplitude. hence the limited idea. Then, just like we've done with the shell filter before, we can combine multiple of these slopes to create a coarsely stepped 3 decibels per octave slope approximation. But first, we'll again have to figure out how a single slope version works. For that, we'll compare it to a basic high pass. You'll notice that the only difference here is this additional resistor after the input capacitor. To understand the effect this has, let's recap the mechanics of a high-pass filter. As the name already implies, a high pass is the exact inverse of a low pass, functionally, but also on the component level. So where the low pass had an input resistor, the high pass has an input capacitor. And the capacitor to ground gets swapped for a resistor to ground. Easy. If you now again think of the capacitor as a charge-dependent resistor, it should become clear why high-frequency oscillations are allowed to pass through, but low frequencies are blocked. Let's imagine that we apply a 2 kHz square wave here. Then the amount of current flowing through the capacitor in the wave's high and low phases is so small that it never builds up a significant amount of charge, which is why its resistance stays very close to 0 the entire time. And in a voltage divider, if the input resistance is very weak in relation to the resistor going to ground, the output voltage will be almost identical to the input voltage. So our high-frequency square wave is allowed to pass through unchanged. Conversely, if the input oscillation was very slow, the capacitor would get charged to the point of completely blocking, cutting out any low-frequency content. Now, by placing a resistor after the capacitor, we give this path a default resistance, just like we've done for the shell filter. The effect is different though. Instead of letting a baseline amount of high frequencies pass through, we set an upper volume limit for them. That's because where before, high frequency oscillations could pass through the cap as if it wasn't even there, now they have to fight this resistance. Heads up though. As a side effect, doing this will move the cutoff point to the left, simply because we also increase the total resistance between our capacitor and ground, causing it to fill up more slowly. To test this, I'll again replace the fixed resistance after the capacitor with a potentiometer. This way, we can dial in different upper volume thresholds on the fly. First up, I'll plug in the input capacitor. Then I'll route the other end through a 100K potentiometer. Slot in a 100K resistor to ground, and we're done. As an input signal, we're again using our white noise to properly visualize the circuit's effects over the entire frequency spectrum. Right now, I've got the potentiometer turned down completely. And here's what happens if I turn it up. As you can see, we're able to set an upper volume threshold for our filter's output, while moving the cutoff point to the left, just as expected. Cool, so we've got the single slope limited high pass down. Next, let's go for multiple slopes. Just like before, we simply have to add in more capacitor-resistor pairs in parallel with the original one, and fine-tune their values until we get a result like this. As we now know, the amount of resistance on the input path in relation to the resistance going to ground will determine the amplitude at which the individual slope maxes out, but also the point at which it starts dropping off. So the values I've chosen here will have our 3 slopes plateau at 150, 1500 and 15,000 Hz respectively, with their maximum volumes set to 1%, 10% and 100%. Again, this is what sounded bluest to me. If you beg to differ, you know how to adjust it now. Finally, we'll only buffer the result instead of amplifying it because it's still very much loud enough coming out of the filter stage. To test this, I'll first set up the 3 capacitor-resistor pairs and connect them to our white noise signal. Then I'll add in the 10K resistor to ground while sending the result into an op-amp buffer. And here's what this sounds and looks like on the spectrum analyzer. As expected, the amplitude gradually falls off towards the low end. Great. So with this, our triple noisemaker is done. Let me know if you have any noise-related ideas you'd like to see me cover in future videos. In the next one, we'll check out a super efficient approach to sawtooth to triangle conversion, using essentially just a single transistor. Until then, you can find a bunch of bonus content on my Patreon page to tide you over. Anyways, thanks for watching, and until next time. See ya!